Learjet 40/45 pressurization system. System, philosophy, structural logic, and core architecture. If you truly want to master the pressurization system on the Learjet 40 and Learjet 45, you must begin with system philosophy. The purpose of the pressurization system is to maintain a safe and comfortable cabin altitude while protecting the aircraft structure. As the aircraft climbs, outside atmospheric pressure decreases rapidly. Without a pressurization system, cabin altitude would climb at the same rate as aircraft altitude. At typical cruise altitudes, that would be physiologically unsafe. The Learjet 40 and Learjet 45 solve this by creating a controlled pressure vessel. The pressurized area extends from the forward pressure bulkhead to the aft pressure bulkhead. Everything inside that sealed volume is part of the pressure vessel. Structural integrity of this area is a primary design concern. The system is not only about comfort, it is about protecting the fuselage from overpressurization or negative pressure conditions. Now here is the fundamental principle you must clearly state in the oral examination. The pressurization system does not primarily control how much air enters the cabin. It controls how much air leaves the cabin. Conditioned air from the environmental control system continuously flows into the cockpit and passenger cabin. Cabin pressure is regulated by controlling the outflow valves, which determine how much air is allowed to escape overboard. This exhaust control philosophy provides smoother and more precise pressure regulation compared to regulating supply air alone. Now let us examine the architecture. The pressurization system consists of the following major elements: cabin pressure controller, pressurization control panel, primary outflow valve, secondary outflow valve, vacuum, jet pump, pressure, relief, protection devices, cabin altitude, and differential pressure indication systems. At the center of the system is the cabin pressure controller. The cabin pressure controller is a dual-channel electronic controller. One channel functions as the primary channel and the other functions as the secondary channel. Each channel has independent sensing capability and independent electrical logic. Channel selection is automatic. If one channel fails, the other channel assumes control immediately without crew input. This is a very important oral examination concept. If a white cabin pressure fail message appears indicating a single channel failure, the system does not revert to manual mode. It does not depressurize. It continues operating automatically using the remaining channel. Only when both channels lose electrical power does the system lose automatic scheduling capability. Understanding this distinction between single channel failure and total controller failure is critical. The cabin pressure controller commands the outflow valves based on aircraft altitude, rate of climb or descent, and selected landing altitude. It continuously compares sensed cabin altitude to program targets and adjusts the outflow valves accordingly. The crew monitors the system through the cabin pressure controller display and through environmental control system indications on the engine indicating and crew alerting system and multifunction display. The three parameters you must always be aware of are cabin altitude, cabin rate of climb or descent, differential pressure. If you understand these three variables, you understand the state of the pressure vessel. Before we move to valve mechanics and vacuum control, remember this. Pressurization is not just airflow management, it is structural management, it is physiological management, and it is automated scheduling driven by the cabin pressure controller. In the next section, we will go deeper into how the outflow valves physically move, how vacuum is generated, and how the system transitions from ground mode to climb mode. Part 2. Outflow valve. Mechanics, vacuum control, and automatic scheduling logic. Now that we understand the philosophy and architecture of the pressurization system, we must examine how it physically controls cabin pressure. The Learjet 40 and Learjet 45 use two outflow valves installed on the forward pressure bulkhead, a primary outflow valve and a secondary outflow valve. These are pneumatically actuated poppet-type valves containing an internal diaphragm. The diaphragm separates control pressure from cabin pressure. Movement of this diaphragm determines how far the valve opens or closes. The valve opening determines how much air is exhausted from the pressure vessel. The cabin pressure controller does not mechanically move the valve. It controls the pressure acting on the diaphragm. This is where the vacuum jet pump becomes essential. The vacuum jet pump is located in the tail cone and is powered by engine bleed air. As bleed air flows through the jet pump, it creates a low pressure region, a vacuum source. This vacuum is routed to the outflow valves and becomes the control medium used to position the diaphragm. By varying vacuum pressure applied to the diaphragm, the cabin pressure controller precisely adjusts valve position. Increasing vacuum pulls the diaphragm in one direction, reducing valve opening. Reducing vacuum allows cabin pressure to push the diaphragm in the opposite direction, increasing valve opening. This pneumatic design allows smooth, proportional control of cabin pressure changes. Now, let us move into automatic scheduling logic. Automatic mode requires electrical power applied, manual pressurization not selected, landing altitude set. When electrical power is applied on the ground, the cabin pressure controller performs a self-test. Any detected faults are enunciated through crew alerting system messages. On takeoff, the system provides takeoff pre-pressurization. This function slightly increases cabin pressure before liftoff. The purpose is to reduce the pressure transient that would otherwise occur when the aircraft rotates and climbs away from the runway. Without pre-pressurization, passengers might feel a noticeable pressure change immediately after liftoff. Once airborne, the cabin pressure controller transitions into climb scheduling. As aircraft altitude increases, outside atmospheric pressure decreases. The controller gradually reduces the outflow valve opening to retain more air inside the pressure vessel. Cabin altitude increases at a controlled rate, typically limited to ensure passenger comfort and structural integrity. During cruise, the system stabilizes. The outflow valves maintain a nearly steady position, holding cabin altitude at the scheduled value while monitoring differential pressure. Maximum differential pressure is approximately 9.7 pounds per square inch differential. The system continuously monitors this value to ensure structural limits are not exceeded. During descents, the cabin pressure controller uses the selected landing altitude to determine cabin descent scheduling. The outflow valves gradually open to allow cabin altitude to increase toward the landing field elevation. If the landing altitude is incorrectly set, cabin scheduling will be incorrect. This is one of the most common oral examination traps. The controller also includes logic for special cases such as takeoff abort and flight abort. In certain ground or low altitude conditions, The system may drive the cabin back toward field elevation if aircraft altitude decreases shortly after liftoff. All of this is handled automatically as long as the system remains in automatic mode and electrical power is available. Understanding this automatic scheduling logic is critical. The system is not reactive. It is predictive. It schedules cabin pressure changes based on aircraft altitude trends and selected landing data. In the next section, we will move into warnings, oxygen deployment thresholds, manual mode behavior, electrical integration, and abnormal scenarios. Part 3. Warning logic, structural protection, electrical integration, and abnormal operation. Now that we understand the mechanical control of the outflow valves and the automatic scheduling logic, we must examine what happens when the system approaches its limits or when abnormal situations occur. Cabin altitude is continuously monitored by the cabin pressure controller. The system uses defined thresholds to progressively alert the crew. At approximately 8,750 feet cabin altitude, the first significant indication occurs. The cabin altitude digital readout begins flashing. Simultaneously, the cabin altitude display on the engine indicating and crew alerting system turns amber and becomes boxed. This is an early caution stage. It is designed to attract attention before the situation becomes critical. If cabin altitude continues to rise and reaches 9,500 feet plus or minus 200 feet, passenger oxygen masks automatically deploy. This number must be memorized exactly. It is not approximate in the oral examination. If cabin altitude continues to increase and reaches 10,000 feet, the oral voice message announces cabin altitude. The cabin altitude indication turns red. This is the critical warning stage and requires immediate crew action. Now let us discuss differential pressure protection. Maximum differential pressure is approximately 9.7 pounds per square inch differential. As differential pressure approaches structural limits, caution messages appear and display colors change. Beyond that threshold, mechanical pressure relief devices protect the aircraft structure. The system includes positive and negative pressure relief valves. The positive pressure relief valve prevents structural overpressurization by venting excess pressure automatically. The negative pressure relief valve prevents structural damage if outside pressure exceeds cabin pressure, such as during rapid descent. These valves operate pneumatically and do not require electrical power or pilot action. Structural protection is independent from scheduling logic. Now let us examine electrical integration. The cabin pressure controller is dual channel. If one channel fails, the remaining channel assumes control automatically. If both channels lose electrical power while airborne, automatic scheduling capability is lost. However, the system does not instantly depressurize. Outflow valve position remains where it was last commanded. Manual pressurization must be selected to regain active control using the manual rate selector knob. After a dual generator failure, the pressurization system remains operational because the secondary channel of the cabin pressure controller is powered by the essential bus. This integration between electrical and pressurization systems is commonly tested in the oral examination. Now let us examine manual mode behavior. When the manual pressurization switch is depressed, A white cabin press manual advisory message appears. White indicates advisory, not malfunction. In manual mode, the crew controls cabin altitude rate directly. The cabin pressure controller no longer schedules cabin altitude automatically. Improper manual control can lead to rapid cabin altitude changes, so active monitoring of cabin altitude and differential pressure is required. Finally, emergency depressurization. When emergency depressurization is selected, both outflow valves are driven toward full open. Cabin altitude increases rapidly toward a preset target. A crew alerting system message is generated to confirm the mode selection. Emergency depressurization is used when rapid cabin ventilation is required, not for routine descent. At this point, you understand the full behavior envelope of the pressurization system: normal operation, protection logic, electrical integration, and abnormal mode transitions. If you can explain these interactions clearly, you are no longer memorizing the system. You are understanding it. Rapid oral review. Pressurization system. What is the primary method used to control cabin pressure? Cabin pressure is controlled by regulating how much air exits through the outflow valves. What provides control force to the outflow valve diaphragms? Vacuum generated by the vacuum jet pump powered by engine bleed air. What happens if one channel of the cabin pressure controller fails? The remaining channel automatically assumes control. Does a single channel failure cause manual mode? No. The system remains in automatic mode. At what cabin altitude do passenger oxygen masks deploy? 9,500 feet plus or minus 200 feet. When does the cabin altitude digital display begin flashing? At approximately 8,750 feet cabin altitude. At what cabin altitude does the oral cabin altitude warning occur? At 10,000 feet cabin altitude. What is maximum differential pressure? Approximately 9.7 pounds per square inch differential. What happens if both channels lose electrical power in flight? Automatic scheduling is lost. Manual pressurization must be selected for active control. What happens during emergency depressurization? Both outflow valves drive toward full open and cabin altitude increases rapidly.